Melissa.
And I'm Jam.
And I'm a chemist.
And I'm not.
And welcome to Chemistry for Your Life.
The podcast helps you understand the chemistry of your everyday life.
Okay, Jam, I've done it to you again.
Wait, then what?
I started to write an episode and then realized that it needed to be 2 episodes.
I'm fine with that. It seems like you're making it sound like you've I don't know, caused a huge inconvenience to me or something. But
I feel like I tricked you. I'm like, we're going to record. And then I'm like, we're going to record 2.
Well, I mean, I think that's fun. So it's plus
Right.
like any story that's 2 or 3 or more parts has a chance of being much more grand and much more exciting. So
That's true.
Seems like the idea of there being a 2-part episode also has that same potential.
That same grandiosity.
Yes, but as long as you can promise on that and like promise beyond the shadow of a doubt that it's going to be that grand, like as grand as say like Lord of the Rings or something like that, some really important story, then I'm in.
Yeah, definitely. This 2-part, maybe 80-minute total, less than 80-minute total episode series is going to be as good as Lord of the Rings for sure.
Wow.
No,
Incredible.
don't. That is false information.
You guys heard it here first.
Okay. So here's where this came from.
Okay.
This was prompted by a listener and friend of the podcast, Erica Davis, LLC, Erica Davis Fitness.
Oh, nice.
So Erica advertised on our show, but she also listens to the show.
Nice.
And let me tell you, this is not an ad. I've been doing her workouts lately, and they kick my butt. They really are good. So go check her out on Instagram. But she messaged me and asked me about Teflon pans. She asked, are they safe? She asked a few other questions. She asked if they're safe, if you can use oil on them.
Mm-hmm.
And she said, I thought I heard about some Teflon danger back in the 80s when it was discovered that their chemicals were causing cancer and birth defects. But we still have nonstick pans. Are they safe to use? And then she also asked about oil on nonstick pans. So, and I knew a little bit about Teflon, but I learned a lot from this, a lot about sort of the history of it. So what I decided to do was first do an episode explaining why nonstick pans are not sticky.
Okay.
And then second, answer her questions about safety and then this back in the 80s, what was going on with these things that we heard. Because I felt like how Teflon pans work all on their own is pretty interesting, but I didn't think we could fit all the history into one episode. And I think it's interesting stuff. So
Yeah. So
it kind of gets into the dark side of chemistry.
is Teflon, like obviously heard that word a lot, but is that the like most common nonstick pan that we have most of us interacted with?
I'm not positive. I mean, yes, I know that Teflon is the first, and it was copyrighted or whatever it's called. What is it called when you invent something and you
Patent?
Yeah, it was patented or trademarked or something like that. Patent probably by DuPont, which is a big chemical company. I know I have met people who've worked with DuPont before. And it was created by DuPont when they were working on something else, actually, refrigerants, I think. And it had all these properties, so they were like, this is great. I'm going to go ahead and use this. And then all this other stuff came out. So, but Teflon is probably the main one. I don't know how I'd even look into be like, is this DuPont Teflon or is this something else? But they were definitely the first. Okay, but right now we're just going to talk about the molecular structure of it.
Okay,
this goes all the way back to intermolecular forces. All the way back. It's the return of intermolecular forces.
Oh, man. This is kind of a saga if you think about it. I mean, we already had a lot of like the Force, Star Wars kind of jokes about intermolecular forces. And then they're coming back.
May the intermolecular forces be with you.
Yeah. And they're coming back again.
It's like the trilogy aspect, sort of.
Yeah.
Like, okay, this is going to be the new episode of intermolecular forces.
Except that we live in a universe where intermolecular forces are a part of it all the time. So the story goes on. It's the infinite trilogy. It's the whatever you want to say.
Okay.
Right?
Yeah. Yeah. I was thinking about it as like, but also the midichlorians, the force is always present in their universe, but we're not in the Star Wars universe as we're experiencing the story. So I agree.
Yeah.
Okay. So we're going all the way back to intermolecular forces. And for those of you who maybe are new to listening or haven't listened in a while to our earlier episodes, intermolecular forces we talk about in What's the Scientific Word for Sticky. We briefly talked about them, I think, in the very first episode about how soap works. And then we talked about it in Why Does Water Form Droplets, I think, too. So intermolecular forces are literally just the forces between molecules, intermolecular, between molecules. And there's a few different kinds of intermolecular forces that we've talked about. So there's the kind where individual molecules have positive and negative parts built in, like permanent. We call them poles, dipoles. And then there's a kind where things are pretty much equally shared, but when that kind of molecule comes into contact with another molecule, there's a temporary, it induces it to have a positive and a negative part.
Is that one dispersion?
Yes, I can't believe you remembered that.
Did also the one, I think you said the sticky ones, but then also specifically the gecko one of those. That one's really interesting, guys. If you haven't heard that one,
oh yeah, how do geckos walk on walls? Right.
Yeah, the forces are there in that case too. So that one's pretty cool.
They're all over the place. So those are the two main ones we've talked about. We've talked about molecules that are polar, and molecules that are nonpolar. And then a special type of dipole moment bonding is a hydrogen bonding, which is basically just the strongest kind of intermolecular force. It's called bonding, but it's not bonding, which is confusing for students and non-students alike. Drives me crazy. If I could change, I would change a lot of things, but if I could just snap my fingers and change one thing about chemistry everywhere, is I would call it hydrogen intermolecular forces. I don't know why that would be so hard. Yeah. Why do we confuse people calling it bonding? Okay, rant over.
Well, maybe even just hydrogen forces. I know it's still kind of confusing, but it's short enough. And it's
hydrogen forces.
Yeah.
Gosh, I'm with you, Jam. That was a good one. Okay, but we didn't talk about something within that. And I remember my students being a little confused by this at the beginning of the last semester. But it is possible, if you have a neutral molecule that doesn't have built-in positives and negatives, but the individual bonds within the molecule can be polar bonds.
Okay.
So you can have polar bonds in a non-polar molecule. So let's think about this. If you have two atoms that are the same, like two fluorine atoms, they're going to be pulling, if they're holding hands and sharing their electrons, they'll be putting the exact same amount of pressure from both sides, and it'll be equal opposite poles. So the electrons will be equally shared.
Okay.
Right?
Right.
So if you had just F2, a fluorine molecule, it's only made up of one bond. That one bond is not polar, and neither is the molecule.
Okay.
Okay. But now I want you to imagine you yourself as a human being.
Okay.
And you're holding hands with one person. If that person yanks on you, you're going to go in that direction. If you're holding hands with two people and both people yank on you equally hard at the same time, you're not going to go anywhere.
Right.
That is what it means when you have polar bonds, but they cancel each other out to make a non-polar molecule.
Oh, interesting.
So when carbon is bonded to something like hydrogen, it pretty much doesn't have a pull on one side or the other. They're just holding hands equally. No one's yanking to one side or the other. But when carbon is bound to fluorine, there's a strong pull towards fluorine. Fluorine is very electronegative, which means it pulls electrons towards it really tightly and close. So it's going to pull as much electron density. The electrons exist in the cloud. It's going to pull as much of the electron shared between the two bonds as it possibly can to itself.
That's fluorine, you said?
That's fluorine.
Okay.
So if you have a carbon and it's bound to fluorine on one side and that's the only bond you have, carbon and fluorine, that's a very polar bond.
Okay.
But if you have a carbon with fluorine on the opposite side, two sides pulling in the opposite directions, those are two polar bonds. But it's a neutral molecule.
Got it. Okay, so that really intense holding on is kind of happening just within that molecule now and not trying to happen outside of the molecule. Like, it's almost like a mom and two kids going through a busy mall. She's holding on tight to her kids and they're navigating through a crowd or whatever. And that really tight grip that she's got going on is just between her and her kids, and not, at least at the moment, not that those forces aren't trying to pull other people toward it. If that makes sense.
Yes, that's exactly right.
Okay.
That's a really good analogy. I'm really impressed.
I was just trying to think, like, how else do you, like, your hands, people holding hands thing, but then how do you, I was trying to make sure that they're not, that then that neutralizes kind of like, they're not trying to grab onto anybody.
Yeah. I also kind of think about it as tug of war. Because bonds are basically just made up of electrons shared between two things, right? So if you have this rope that represents the electrons and there's a flag for like it being perfectly shared in the middle between the two, then if you pull on one side, the flag's going to move towards that thing, and that's a polar bond. But if you, this is where it kind of breaks down to get into the polar molecule. If you had something else that starts pulling back again the opposite way from the even further down, that little flag is going to come back to be right in the middle again. But I think your analogy was better. So it's just all, chemistry is all about electrons, man. And in this case, we're talking about the way the electrons move inside the molecule, but how that doesn't change the overall polarity of the molecule, like you said.
Yeah.
Okay.
Gosh, this is interesting. There's layers. There's always layers.
There's always layers. So Teflon is a polymer. Do you remember? You can put what I just said about the molecules on the shelf, and we're going to go to Teflon now. Okay. So you've got your molecules, your polar bonds, and your polar molecules there on the shelf. And we're going to examine Teflon, which is a polymer. And we talked about polymers. I don't remember which episode.
Maillard
reaction, yes.
So brown stuff or whatever is what we call that one, I think.
Why does toast get toasty?
Oh, yeah. And then also, wasn't the polymer the apples?
Yes, apples are polymers too. And I want to remind you, you said this, and I remembered it because it was so good, that a polymer is a big molecule made up of a bunch of repeating molecules.
I'm glad that you remember that. That's
it's so good.
It's helpful for me to hear my own thing again.
So it's just a bunch of repeating units. So it was like ABC, 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 and they're all bonded together in one long chain.
Got it.
That's a polymer.
Okay. Man, I'm so glad that you reminded me, and also with my own words, because like sometimes, like, you know how you find a note you wrote to yourself or something, like a little sticky note?
Yeah.
Hearing it from yourself, like your past self, trying to be like, listen, don't drink this. This one, this is the old, this is the old ketchup. Don't use this one or something like that. I don't know.
Right.
It's just like, yes, right. Of course, my past self is trying to protect me.
You understand the way your brain works, so when you hear your own words, you're like, yep, I got this.
Okay, so ABC, ABC, ABC. Got it. Okay.
Right. It's a repeating unit.
Right.
So in the case of Teflon, it, instead of ABC, ABC, it's a repeating unit of a carbon bonded to two fluorines. And then that's bonded to another carbon. It's bonded to two fluorines. And that's bonded to another carbon. It's bonded to two fluorines. And it just goes on and on and on like that.
Okay.
So it's a polymer made up of that one unit.
Okay.
They call it, I can't remember. It's like a monomeric polymer or something like that.
And that's the I know you put the intermolecular forces on the shelf, the polarity stuff on the shelf, but this is that same molecule, right? That is really good bonding together, but is not polar as a whole. Like it's made up of polar bonds, but it is not trying to get all polar with other folks.
Right. So, and Teflon is extra special because fluorine is the measure of how closely the electrons are held in. Like I said before, is called electronegativity.
Uh-huh.
So fluorine is the most electronegative atom.
Okay. Wow.
So fluorine holds electrons towards it better than anyone else.
Okay.
So you've got this Teflon polymer, and it's basically a carbon chain surrounded by fluorines.
Mm-hmm.
And those fluorines are holding electrons so tight to each other that basically when two of those molecules come in close, or when that molecule comes in close to another one, it's barely going to induce that polarity at all.
Mm-hmm.
Because it's holding its electrons so tight, it will not do its normal dispersion forces.
Huh.
What are you thinking?
Just trying to get my head around it. But so you said it's holding on so tightly that it won't do its normal forces. So basically, it's kind of commandeered all of the available force or something. I don't know.
Well, so we talked about dispersion forces, which are just the forces that are temporary when two molecules come near each other, right?
Mm-hmm.
So in the case of Teflon, if it comes near another molecule, it's holding on so tight to its electrons with those fluorines that it does barely any temporary polarity at all.
Got it. I was not zooming out to see how that's going to end up being helpful to food related stuff. I was just like still way in there molecularly.
Right. Okay, so zooming back out. So we know that Teflon is this carbon chain surrounded by fluorines. And so even though those individual bonds are very polar and tightly held together, the overall molecule is just neutral because they're pulling in opposite directions. So all of that cancels out. So it's a very non-polar molecule. And it's holding on so tightly, the fluorines are holding on so tightly to the electrons that they can't really move around at all when it comes into contact with another molecule.
Got it.
So there's not going to be very many intermolecular forces between Teflon and anything else because it's holding on so tight to its electrons.
Okay, got it. Yeah, interesting.
The word for that, the ability to sort of the electrons to shift around when it comes near something else, is called polarizability.
Whoa.
And Teflon basically has none.
Okay.
Okay.
Huh.
So because of that, Teflon doesn't interact with anything else.
Man.
And that's why it's nonstick.
Man, that's crazy.
I know.
Huh. Like it's weird how kind of, I mean, it's not simple, but it's weird how at the molecular level, it is kind of simple. And then the result is something that for us is an everyday like usefulness that
I know. Isn't that crazy?
It's just kind of like all these things end up being the byproduct of inherent chemistry, you know?
Yeah, it really is like you're saying, oh, this is so simple. But the very first time we talked about intermolecular forces, it was not simple.
And this isn't even really that simple at all, but I think it's kind of like the application of it to get food to not stick to stuff is you kind of think like, man, that must be hard or complicated. But
right.
the molecules are doing something super complicated that we aren't in charge of. We're just kind of taking advantage of, I guess is what I mean. So it's not like scientists found some like God particle that they harnessed into made it into a pan. I don't know. You know what I mean? It's like they just, this is a thing that already happens and we are using it to our advantage is kind of, I guess what I mean.
Yeah. So that's pretty much it. That's how Teflon pans work is they create a polymer and they put it on the stainless steel or aluminum pan or whatever. And that basically creates a barrier that is not able to basically interact molecularly with anything else really. And so things don't stick to it and we can just wash them off away.
Okay, I think I got it. So basically, like we started with the intermolecular forces, just good to know that in this case, fluorine, super, super strong electronegativity, which means it wants to draw electrons to itself.
Right. It's selfish.
It's very selfish because it lacks a lot, right? Is that normally how it is?
I mean, that's kind of a more complicated answer. Most people will learn about electronegativity and why it is the way it is in first semester of chemistry. I think it would be too confusing and off topic for our conversation today to try to dig into that.
Got it. Okay, got it.
I mean, we can talk about it, but I think it would just be like, okay, now we're getting into atomic trends and how an atom builds up and all of that. And that might not be as fun as talking about Teflon. So
right.
We can save that for another day, I think.
Okay, that sounds good.
Great.
So it's very electronegative. And in this case, it is, what it is drawing to it is carbon, right? And whenever you have a situation, go ahead.
It might be maybe a little bit more accurate to say it's drawing to it the electrons in the shared bond with carbon.
Got it.
But I think it does bring the carbon itself closer to. I think those stronger bonds will bring you closer together.
So it really wants, in this case, carbon's electrons, which draws carbon to it, and they bond together. And even though that really strong electronegativity that fluorine has is super strong, once it is in a situation like we've been talking about it, where it has 2 fluorines and 1 carbon, they're so, is that right?
Yeah.
Okay. They're so in their own zone and like really strongly attached to each other that they are not worried about trying to draw any other electrons to themselves. They're like, we've got our carbon. We've got what we want. We only have eyes for carbon.
That's a good way to put it, that we only have eyes for carbon, because the fluorine's pulling so hard on each of the fluorines pulling so hard, but they're pulling against each other that they're not going anywhere.
Yeah.
So it makes the overall molecule so nonpolar that it's not interacting with anything else. So even though those bonds individually are very like negative, positive going on, they just cancel each other out. And so they're like, we are totally happy. We don't need to have any induced dipole, nor can we even.
Yeah. And then they're in this happy situation. And so you get, that's just looking at one molecule of carbon and 2 fluorines, right? But
so in real life, carbon needs 4 things bonded around it. So it usually is carbon, 2 fluorines, and then 2 carbons opposite each other. And those 2 carbons have 2 fluorines and then a carbon on either side of it. So it's a chain of carbons. But if you just zoomed in on one carbon, you could see those 2 fluorines attached to it, and then it'd be holding hands with other carbons off to the side. But those also kind of cancel each other out. So that's a little, deeper than you need to go. So I think just talking about imagining one carbon with the 2 things pulling on opposite sides is the easiest way to think about it.
Got it. It's a lot easier to think about a mom with 2 kids than to try to think about a mom and dad and 4 kids trying to navigate them all. It's like,
it'd have to be a mom with like 4 hands exactly opposite from each other pulling in exactly opposite directions. So that's too confusing.
Yeah, most moms wish they had that many arms, but they do not.
That's so true. Moms are like, man, that'd be great.
Yeah, they're like, man, if only I was a molecule or whatever. I don't know.
If only I was carbon and could make 4 bonds instead of just 2. Yeah.
So mom's moving through the mall with the kids, and the bonds are so strong that the eyes, the effort is all concentrated on staying together, that they are just not concerned about the other elements and other electrons around. They're focused on each other, kind of thing.
Yeah.
And they made a polymer out of just tons of this exact thing, repeating over and over and over and over and over and over and over. So just this coat of this stuff. So you've got all these moms with their kids moving through the mall, And so even if you crack an egg on top of these moms, they are so only worried about getting through the crowd with their kids that there's no dispersion forces or no other kind of forces available to interact with this egg.
I love how you mixed your metaphors there. But that's right. And I almost think of it as like a force field. Mm-hmm. So these fluorine atoms are so non-polarizable. They just can't be wiggled around because the fluorine's holding on so tightly that you just create like a force field almost above the top of you, and nothing can get in. Mm-hmm. You know, it's just, we're not interested. There's very little interaction that's going to happen. Yeah. It's like, we're not worried about it. We're just totally holding on to our own things, and therefore we're not very polarizable.
Yeah. Like when you were explaining that part earlier, I was kind of thinking about like somebody who's like newly in love, like smitten. They're like, there's just like this force field going on where they're just like goo for this one person or whatever. And so in this case, if it was like that, it's like there's just no way for something to get in here. It's as if that like really early, like overwhelmingly smitten kind of stage, it's as if that stage of love was just permanent and that intense for this coating on the pan, where nothing can break into it, nothing can like, or whatever. And that's not a statement about love. It's just like that level of intensity where it's like, oh, I can only think about and like focus on this other person. It just, nothing else matters. Nothing else in my entire life matters. And then it's like cracking an egg, throwing the bacon, whatever it is you're putting on there. Obviously, our foods are made up of a lot of different things, but it doesn't matter in this case because there's that force field. It's not trying to interact with any other thing.
Right. I think that's a pretty good explanation. It's kind of hard to come up with a good, I think, perfect metaphor because it's so many layers.
Yeah.
But just to like sort of zoom back out and remind you of like we talked about intermolecular forces. Mm-hmm. And so this is a nonpolar molecule, mm-hmm. but most nonpolar molecules will come together and have an instantaneous dipole with one another. Mm-hmm. But this is an also non-polarizable molecule. Mm-hmm. So it can't even really do that. I mean, it can to some extent, but not a lot. And you can see that play out once you coat a Teflon pan, mm-hmm. because if you put water on it, it rolls right off. But if you put oil and grease, it sticks to it a little bit better. Mm-hmm. And that's because the nonpolar can a little bit interact with other nonpolars, not very effectively, and all of it will come off easily.
Right.
So there's layers of that. So you learned a new thing, and you combined old things with the new thing.
Yeah.
I think because it's kind of a complex one, I just felt better about coming back and kind of pointing out some of the stuff and how it all works together.
Right.
So
there's multiple things. It's not like one explanation is going on intermolecularly. It's like a compounding of multiple. That's so crazy.
Right. So there's one question that it didn't even occur to me, I guess, to ask until I found an article about mm-hmm. it. And that is, if Teflon doesn't stick to anything, how do we stick it to the pan?
Oh my gosh, seriously.
It's a really complicated process, but basically they chemically treat one side, so they alter part of the polymer and stick it on there. There's a Scientific American article about it, and it was not interesting enough for me to want to share. Uh-huh. It was like too complicated, would have been too hard. But I thought, yeah, why aren't we all asking that question?
Yeah. Gosh, that is interesting.
So maybe one day I can go and find a good story in the saga of how you stick Teflon to something when Teflon doesn't stick to anything. But
that's one of those things where it's like,
not today.
I love that question, even if the answer's like a lot to go into. It kind of reminds me of the part in the movie, in like some movie, I can't think of what, or maybe many, where the characters are like, wait a second, if we're back here, then who's driving the bus? Like that kind of question, like, and then they realize that the bus is like careening off a cliff or
like Pirates of the Caribbean, or he's like, no survivors. Then where do the stories come from?
Yeah.
And you're like, yeah, where do the stories come from?
Yeah. It's like it's like a really frustrating question almost. It's like, wait, so can I trust anything? Like, how can we get this to stick to the pan? Like, what good is it to have this awesome polymer if we can't get it to stick to anything?
Right.
Even the things we want it to stick it to. It's like, why can't we just pick and choose? Which I guess they did figure out how to do that.
Yeah. Okay, so
there were no survivors.
There were no survivors. Where do the stories come from? Well, that's pretty much it. That's all I've got for you in terms of science today. So thanks for coming and learning about that. And do you want to tell me something fun about your week?
Anytime. And yes. So this week, something that was kind of cool that I really ended up enjoying is Em and I are trying to get our nursery ready.
Oh, yeah.
And so we've had more time on our hands, but also some things are harder to do. Like, you know, a lot of people are posting stuff about like projects around the house. We're not the handiest people in the world, but something we've been wanting to do anyway, because ready or not, our baby's coming. And so we've been dragging our feet because we needed to paint in here, and it's a small room, but that's where I'm recording right now, which is why I said in here. And it's just a horrible yellowy color, and we've already gotten rid of this color in other parts of our house. And so it's just like yet another area where we have to get rid of this really bad like buttercream color. So this week we
I think buttercream is less yellow than your walls.
It might be. It feels like there's a lot of, like, I don't know what else to describe it as. It's like a very creamy, buttery like look to it. Sometimes people say cream and it's like more like white, like it's just slightly not white. But this is like,
but this is pretty yellow.
Yeah.
It's like almost like whipped butter.
Mm-hmm. Yes. Yeah. So this week we really started working on that, and I finished a full 2 coats of just the main walls, and then we're going to paint the trim and the shelves and stuff like that in here. But what was just nice about it is I think I just really enjoyed it because it was doing something with my hands, and a lot of us have been way, way, way more on computer and phone than we already normally are, which is pretty high already. And so coming in here, and my wife's pregnant, so she can't paint. And so it's just me alone, but doing something with my hands and just focusing on a task that was very, very physical. And I was like listening to podcasts and music while I was doing it. It was just like strangely very enjoyable. And so I was trying to take advantage of that momentum of like enjoying it and thinking about it in that light all the way through finishing this project. So
I could see that. I could see how that would be really a nice thing. My roommate and I have been going on bike rides, and it is just nice to do something with your hands and body and like accomplish a goal, you know? So
totally. It really is.
I could see how that would be really nice in the weird age of isolation.
Yeah.
I think I'm going to do. So we shared a few weeks ago about how my mom passed away, but we record these episodes a little bit closer together. So it still feels a little bit new for me. Like, I think right now it's been maybe like 2 weeks or so. So it's still pretty fresh, and people have just been so kind. And I just wanted to kind of talk a little bit about that, about people have been so kind and loving. Even with coronavirus, 2 different people have sent me cookie deliveries.
Nice.
Which, if anyone you know is sad, don't send flowers, send cookies.
Oh, for sure. Absolutely.
It was the nicest thing both times. I was so delighted. It was just so exciting.
That's a much safer bet too. I mean, like people may like kind of like flowers or may love them, but everyone likes cookies. Surely, you know?
And I could share them with my roommates, so that's been nice. Or I posted about this on Twitter, but I can repost it. Some of my close friends, I lived with them for a while. They have 2 kids, and they mailed me letters. And the little girl drew a picture of us doing science together because I do science experiments with them a lot. And the little boy drew a picture of Victory Green, who's the Dallas Stars mascot. He did a good job. So just little things like that where people have just been so kind, and thought of me and tried to think of ways to be with me, even from far away, kind of trying to be wise and smart and follow the order, just makes me think about how thankful I am for the awesome friends and community that I have around me. And it's just been really nice. It's been a nice thing to be able to spend time with people. And so sort of spend time with them remotely. I don't know.
Yeah.
That's been really special to me. So, and again, send cookies. You guys don't have to send them to me. I mean, to anyone who's sad ever, just send them cookies.
Yeah. Yeah.
I think that's my happy thing for the week, is just being really glad that I have really awesome friends who are so kind and thoughtful and are creatively coming up with ways to feel close.
Yeah, absolutely. That makes sense. It's awesome.
So, all right. Well, I'm glad that you were so excited to learn about teflon and came up with your creative mixed metaphors there.
Yeah, it's kind of funny because I guess that makes sense because, like you were saying, there's a lot of layers of molecular stuff going on. It's not just one thing, which is kind of why maybe one metaphor doesn't work great. We had to use like 3 or whatever.
Yeah, but it's so funny. The idea of a force field of moms at the mall with an egg being poured over top of them is hysterical to me. So
that mental picture
just like floats above them and is slowly getting cooked or whatever.
Yeah.
And then also I want to thank the listeners for coming and listening and learning about what makes nonstick pans not sticky. It's always such a joy.
Melissa and I have a lot of ideas for topics of chemistry in everyday life, but we want to hear from you. So just like the Teflon idea, if you have questions or ideas, you can reach out to us at Gmail, on Twitter, Instagram, and Facebook at Chem for Your Life. That's Chem, F-O-R, Your Life, to share your thoughts and ideas. If you enjoy this podcast, you can subscribe on your favorite podcast app. And if you really like it, you can write a review on Apple Podcasts. That helps us to be able to share chemistry with even more people. If you'd like to help us keep our show going and contribute to cover the costs of making it, go to ko-fi.com/chemforyourlife and donate the cost of a cup of coffee.
This episode of Chemistry for Your Life is created by Melissa Collini and Jam Robinson. And references for this episode can be found in our show notes or on our website. And we'd like to give a special thanks to A. Collini and A. Kiwasong, who reviewed this episode.